Hello everyone, and welcome to the first tutorial of NIRx's virtual fNIRS training course, which will be focusing on sending triggers. Okay, so for over 20 years at NIRx, we have designed and manufactured innovative fNIRS devices and software. We integrate our devices, software, and more into user-friendly and powerful research solutions. Our team of scientific consultants focuses on providing you and your team with training and outstanding support so you can focus on your research. This course is one example. Our fNIRS solutions are invented, designed, and manufactured in Berlin, Germany, distributed by a network of excellent local distributors worldwide, and supported by an international team of scientists in Europe, North America, Australia as well, represented here today. So joining me today, well, first off, my name is Ashlyn Casey. I'm a support consultant with NIRx based out of the US. I'm joined by Dr. David Medine, who's joining us from Australia. He is one of the founders of LSL, so we're very grateful to have him here today to answer some of our questions. And as well as Amy. Amy Young is a marketing associate with NIRx, and we're very happy to have her helping us today. Okay, so we'll say goodbye to Amy and David, and we can start focusing on the presentation here. So you are muted. Questions are welcome at any time via the Q&A panel in the GoToWebinar interface. Content will be available on our support site in the upcoming days. Now, for the entire course, all of the recordings, slides, pre-materials, post-materials are going to be available at this link, the course resource page, which is hosted on our support site. This information was sent to you in previous emails and correspondence, and how to register for the site, and this link as well. But if you're missing any of these steps, please send us an email at consulting@nirx.net, and we'll make sure that you get all the information and resources that you need. Okay, so just to orient ourselves a little bit, where are we in the course? As I mentioned, today is the first tutorial. We did have one tutorial earlier today for the earlier time slot. But the first tutorial content-wise, tomorrow we'll be having a lecture on fNIRS data analysis by Dr. Paola Pinti. This is going to be an excellent webinar to attend. Dr. Pinti is a leader in fNIRS analysis methods, and there are some pre-materials to review before the course available on our course resource page. And here are our social media tags, so you can join us on our journey in various platforms. Moving right along into the meat of today, sending triggers with LSL and TTL. So the purpose of this tutorial, first we'll cover the need for sending triggers. What are they? Why are they important? And we'll touch upon the basics of synchronization. We'll discuss more technical implementation of triggers via hardware or TTL, using software or LSL, as well as manual triggers, which is basically sending triggers via keyboard stroke. And we'll round it out with a hands-on portion illustrating how triggers can be sent via LSL using PsychoPy and Aurora, the NIRsport 2 recording software. So this tutorial will get into some details. The goal at the end of it is to give you at least an idea of what triggers are and the basic means of implementing them. As far as details go, you do not have to memorize this, of course. It's more to just present the information now, and then you can come back to it later when it actually is time to send triggers when you're setting up your paradigm. So the need for sending triggers. Continuous wave fNIRS measures changes in hemoglobin as a result of behavioral changes, changes in the environment, or both. It's critical to register the onset of these stimuli. This is the term for registering these events, and basically the manifestation of it is going to be event markers, synonymous with triggers or timestamps. And these are things that are going to be marked in the data. So in your fNIRS data, you need to mark when things happened externally. And for each condition that you have, each distinct condition type, you're going to have a separate trigger value. So say you have a left and right finger tapping paradigm, you're going to have a trigger for condition 1, that's the left. The left condition, you're going to send a 1 every time that condition happens. And then for your right finger tapping, every time that condition happens, you're going to send a 2. The basics of synchronization. So independent of the experimental design chosen and the stimulus presentation software used, it's essential to know when stimuli were shown to the participant. For some research methodologies, you will need higher timing accuracy than fNIRS. fNIRS has a lower temporal resolution, so you don't have to have as precise timing. Now, why is that? Well, it's because the hemodynamic response in fNIRS occurs over a longer time scale. We're talking seconds, not milliseconds, as is the case in EEG or MEG research. And to give you some practical details here, the sampling frequency of a NIRS port 2 with a standard illumination pattern is 8.7 Hertz. That of a NIRS Scout is 7.81 Hertz, which corresponds to a time sample of 114 milliseconds and 128 milliseconds, respectively. So what that means is, so long as your trigger is being registered within that 100 millisecond window, you're fine. It can't get any more accurate than that when it comes to analyzing the data with fNIRS. So you generally do not need millisecond accuracy in fNIRS as is required in EEG ERP research, say. But importantly, you don't want to be adding significant variable time delays, which could add an effect to your data. So you don't want to be sending triggers that are, a second or 3 seconds off from each other that could introduce an unwanted effect in your data. Okay, so sending triggers using hardware. So first we're going to talk about one implementation of sending triggers, and that is using TTL, transistor logic, and we'll talk about solutions for this as well as multimodal imaging. So here we have a representation of sending TTL triggers. So TTL is basically an electrical pulse sent from one system to another, which means it's going to have very high temporal resolution. The subject in this image is viewing a checkerboard stimuli from a computer, and that computer is sending out a TTL pulse via cables to the NIRx device. Now, what triggers can be received, so what values can be encoded in this signal are going to depend on the device. So in the case of the NIRS Port 2 and NIRS Scout X, those are going to be integers 0 through 255. For NIRS Scout or NIRS Port, that's integers 0 through 15. So what that means is that TTL pulse is going to encode any integer within this range. If it sends a character or something outside of this range or a floating point, it won't be registered by the system. That's just inherent of this hardware. And other neurophysiological devices will similarly have some kind of restrictions on this. Okay, so more about TTL. TTL signals are generally sent over the LPT port or the parallel port, also known as the D25 port or the printer cable port. It kind of is a bit of a vestigial organ when it comes to computers. I mean, it still does have function, but at one point it was available on all desktops and many laptops as well. These days it's not as common, but it is a standard in neuroscience research. A lot of devices still use it. Fortunately, there are some practical ways around this, as we'll discuss. But just to show you, this is what that LPT port looks like. NIRx instruments either have a 4 or 8-bit TTL input, and that's referring back to that integer range of what it can receive. Generally, in every lab, there is a dedicated stimulation PC with an LPT output port. Now, I would kind of rephrase that and say in every established neuroscience lab, you'll have one because it's just kind of a standard to have, but in newer neuroscience labs or labs with newer computers, it's rare to have the LPT port. But should you have it, all you need to do is connect the LPT port on the stimulus presentation computer to the NIRx imager via a cable that NIRx provides you with when you get the system. So here is a diagram kind of putting it all together. We have a stimulus presentation PC presenting the stimuli to the subject. At the same time, a TTL pulse is sent out via the provided cable to either via the TTL port that's on the computer or an intermediary device, as we'll discuss. That then connects to the NIRx fNIRS device and finally to your data recording software. So that is the loop. So what if there is no LPT port on the PC? There are no simple converters that we would recommend using. You do have kind of USB to LPT port readily available for like $25 from Amazon. But the problem is those aren't dedicated for neurophysiological research. They're going to have variable timing delays, and they can significantly impact your data. So instead, we recommend some various hardware. The Cedar C-Pod or the Stim Tracker are going to send out, they can do the conversion for you from USB to parallel port output or LPT output. And the Brain Products Trigger Box can do the same, all with little to no timing delays. Another option is to use an Express DB25 LPT card that are available for desktops and laptops. So you can actually insert the port into the motherboard of some computers, not all. This is something you're going to want to confer with your IT department on. Okay, so now in this image, we're just showing how basically the C-Pod, if you don't have the LPT port on your computer, you can use something like the C-Pod or the trigger, the Brain Products trigger box in the middle in order to take that signal from a USB output into the LPT input on the NIRx device. Okay, TTL and multimodality. So if you want to synchronize triggers via hardware to multiple devices, say you have an EEG system as well as a eye tracking device, and you want triggers to be sent out at the same time to all three of your devices, NIRx offers the parallel port replicator box. This is a separate accessory. It's about this big, not very big at all, that has one input and 4 outputs. And so the input is going to be from the stimulus presentations PC, and the output is going to be into the various neurophysiological devices like your EEG, your fNIRS, your eye tracking, and so on, so that you can record simultaneous triggers. Okay, and then I just want to mention as well manual triggers. So it is possible to, with NIRx devices, to insert triggers yourself as the experimenter using keys F1 through F12 on your keyboard. Specifically for the NIRSport 2, our other devices accept these ranges of F1 through F8 keys. So if you press F1 while you're recording, you're going to get a timestamp marked with a 1 in your data. Now, these are not as precise, so when it comes to actually registering when something happened, you've got to consider the delays of human perception as well as the delay of the keyboard, which is not as precise of a timing instrument. So it's more recommended for taking notes than marking when things actually happened. So for example, if you want to take a note, this is where the subject took a break. You hit the F1 key so that you know later in your analysis not to analyze that data. Another reason might be if you're doing a functional connectivity study and you just need to roughly know when the experiment started. But outside of these general examples, certainly when you're sending a lot of triggers and you need to know the precise timing, we don't recommend using manual triggers. Okay, now to talk about software implementation of triggering. So to implement software triggers, we'll be using LSL. So we're going to talk about what LSL is, its core components and distribution, as well as supported devices and tools. Okay, so what is Lab Streaming Layer, or LSL? A definition is that it's a system for the unified collection of time series in research experiments. It handles the networking, time synchronization, near real-time access, as well as optionally the centralized collection, viewing, and disk recording of data. So basically, it does a whole lot of things. It was developed at the University of San Diego to empower mobile brain body imaging in 2012. So it was really done to seamlessly connect all these various instruments that were trying to record a body in motion, including neurophysiological measurements, peripheral measurements, and so on. And it wanted to do that in a seamless way without all these tangle of cables. So basically, LSL was created so that these various software applications could talk to each other without the need for all these cables. Its current state, it is open to all, it's open source. It's available at this link on GitHub, and it has documentation at this link as well. It's open to everyone, so as a researcher, you can easily implement it in your code, as well as manufacturers are also free to implement it in their commercial software. And that's a really big benefit because then you've got, it's kind of more of a standard. If it's open to everyone, including people who are selling neurophysiological devices, that means it's just going to be more prolific and easier to collaborate between various devices. It's really, really taken off in the last couple of years because of how easy it is to use. There are a couple stipulations with LSL. To be connected, all softwares must share the same network. That could be the same internet connection. It could also just be on the same computer. All softwares must have access to and interface with the LSL library. All softwares must also know the variable names of the LSL streams, as we'll see in the hands-on portion. So as I mentioned, LSL does a lot, like collecting data from various sources and encoding them. But our primary focus today is going to be triggering via LSL. And we're also going to touch upon real-time data streaming because they are two things that are readily available with NIRx software. Okay, so here we have a diagram of LSL, this kind of magical thing I've been talking about. What is it? Well, down here we've got a computer and a cell phone, and one could be running stimulus presentation software, the other could be running data acquisition software. Well, the core of LSL is a network protocol, library, and various language interfaces. It ensures that the data is sent and received in a way that all parties understand. The user doesn't have to deal with any of the network connectivity issues. The connectivity is taken care of by the liblsl library. And on top of that, there are a number of program wrappers so that the developer can use any language they're comfortable with to acquire or send data and triggers. So this is important. Say if you want to send your data, want to send triggers via CyclePy and Python, and then you want to receive them in MATLAB to do data analysis with. LSL software distribution. So the LSL software distribution includes documentation, user guides, example programs, acquisition programs, and generic tools. So there's a lot to work with that help you with practically implementing this library. As I mentioned, many acquisition programs come with LSL embedded. There's also some generic viewers and recorders available. And finally, there's lots of example code and documentation to help you integrate LSL into your own code and applications. And what's nice about this is that even though LSL is really complex, the examples that you're given to integrate the LSL library are super easy. You generally just copy and paste them, and it works pretty seamlessly. Okay, just to give you an idea, if you're really kind of averse to anything that has to do with any kind of coding, there are plenty of devices, as I mentioned, manufactured that come with LSL in them. Here's a list of EEG devices, eye trackers, motion captures, human interface, and multimedia devices, as well as some just pure software applications like stimulus presentation softwares. And you could include NIRx devices on that list of hardware that supports LSL. Okay, now we're going to go, I'm going to give a practical overview of integrating LSL into NIRx products, because that's what we'll be seeing in the hands-on portion here. So sending triggers over LSL and receiving triggers over LSL is what I'll be showing. I'll be using CyclePy, a stimulus presentation software, to send the triggers. We'll be focusing more on CyclePy next week on Thursday's tutorial. So we won't be focusing so much. I'll just be showing you briefly what we need to do to sync up the trigger stream in CyclePy. Okay, so coming to the data acquisition software, what you need to do is you just need to really declare that the name of the trigger stream in your recording configuration. So to do that, you go to Edit Configuration, LSL Stream Names, and you specify the trigger in stream name in the box provided. And then you're given the option of testing the connection. So you can do this so that you know that triggers can freely flow from your stimulus presentation software to your recording software. You also have the option of specifying the data out stream name for streaming data via LSL. In NIRS Star, for NIRS Scout and NIRS Sport devices, you're going to go to Hardware Configuration, Data Streaming, Receive Triggers via LSL. You need to enable this. You need to select receive triggers and basically click yes. You need to declare the stream name as well here. And you also have the option of testing the connection. Now, as for switching gears to streaming data via LSL, so in Aurora, that's done by default. You don't have to do anything. Every time you hit record on Aurora, the data is sent out via LSL. Here you're given what the structure is generally. This is also detailed in the user manual. But basically, Aurora streams, no matter what, the raw and the raw data and the data converted into oxy and deoxyhemoglobin. So this can then be used in Turbosatori, which is a dedicated real-time analysis software, or MATLAB or Python to analyze your data in real time. For those of you not familiar with real-time analysis, this is something that if you're running a BCI experiment or neurofeedback where you want to show the subject, for example, what's going on in their own brain, that's why you might use real-time analysis. But if you're not so familiar with it, you don't have to worry yourself about it. Okay, Coming to NIRx sending data via LSL, you do have to just enable it really quickly in NIRx by going to hardware configuration, data streaming, live streaming layer, and just click enable LSL. And in NIRx, you get the option of specifying if you want to put out the converted data or the raw data or both. Okay, and now I'm going to transition to the hands-on portion. I'm going to show you how to send triggers to your NIRx Port 2 device using LSL. Sorry, sending triggers to Aurora and your NIRx Port 2 device using LSL. Okay, so now I'll just show you here. I have my NIRx Port 2 device connected via USB cable. So I'm just going to put that off to the side. And let's see, I want to come to Aurora. And I'm going to select my device here. I'm going to select my configuration. I'm going to use this motor 16 configuration. I want to go to edit and LSL stream names. So this is where I'm going to specify the name of my LSL stream. So it has to be the same here and in my stimulus presentation software. I believe, let's go ahead and change this just for the sake of changing it to trigger. And now I'm going to come to PsychoPy, which is my stimulus presentation software of choice. I'm going to come to the load LSL object, this custom code object, see where it is. I've kind of got my screens mixed up here. I'll just have to close this and open it out again. Okay, I'm just opening up my PsychoPy again. Taking its time. Okay, so here we have our PsychoPy GUI. I'm gonna go to the load LSL object and click on this code object. And here again, we're gonna go over this in more detail in the PsychoPy tutorial, but basically I just need to initialize my LSL stream here. And one of the parameters that's needed is the name of the trigger stream. So we change that to trigger, and that is actually the name of the stream here. So whatever I have in Aurora, I need to have here so that the two can communicate basically. I'll click OK. This is basically, this is a quick, this is a rapid finger tapping experiment here, where we've got a trigger 1 being sent out for the left condition and a trigger value 2 being sent out for the right. So if I go to my start trial and I check out the code object here, I see that the value marker is being pushed out, and that's going to correspond to 1 or 2 for either condition. Okay, and we'll see that when we record the data in Aurora. So what I'm going to do now is hit run. And as this is generating the script, click OK. Okay, so the script is first going to be paused, and I'm going to get the instruction that I should check the LSL connection. So I've inserted this into my PsychoPy code to give me a breather, so I can first check in Aurora if my stream is connected. So I can come over here and select test connection. Sorry, the pop-ups are not happy with my screen share. Okay. No, I don't want to close. Let me just change my GoToMeeting sharing settings. Okay, this is what I wanted to show you. This pop-up comes up now that just says that the trigger stream was successfully connected. So that is what you should see so that you know that the LSL stream was in fact connected to. So we can select OK and hit save. I'm now going to move on with this recording, select this configuration. Okay, I'm going to skip calibration. Right now, my device doesn't have any probes in it. I'm just going to be collecting electrical noise. And I'm going to skip to the recording section. Click yes, click start. Okay, so here we have the data streaming. And now what I can do is I can go ahead and start my experiment in PsychoPy. And that's going to happen by clicking the space bar. And so you're going to see when this flashes left, a blue marker show up. And when it says right, an orange marker is going to show up. So those correspond to the integers 1 and 2. And so that's how timestamps are going to appear during recording. They're just going to be lines down the center of your data. So you're going to want to look for this when you're recording to make sure you know that your triggers are actually appearing. And you're also told information about the incoming triggers down here. This is going to be the same manifestation for hardware triggers. They're also going to appear as a line down the screen. And then what we can do is we can close this script. It's done its duty for us. We can stop this recording. And let's see what the triggers look like in the data set. So it's nice to see visually, what happened, but what actually is, being recorded in our data. Well, if we head to our Aurora directory, we go to the data we just recorded. This TRI file, stands for trigger, is here. So I can open this up and I see that I have this log of the time in UTC code when something occurred, the data frame relative to the onset of the recording that it occurred, and the value of the trigger. So it was an integer 1 and then 2, 1 and then 2, 1 and 2, and so on. Now this file you're not really going to use actually. Most likely you're more likely to use something like the .NIRs or the .snrf file for the rest of your analysis, because that kind of integrates nicely your triggers, your montage, your data, and so on. But yeah, so just to wrap up, the important takeaways here are that we use PsychoPy to establish an LSL connection, and we sent triggers via LSL. They were received in Aurora. We saw them visually happening, and that was a nice sanity check. And then we checked the data, and we saw that they were in fact there and recorded relative to the starting and stopping of the fNIRS data. So that is all that I have to share as it comes to the presentation. So now I will invite David to join us once again. And we can start to answer some questions. Hello, welcome back. So let me go ahead. I'm going to pop up the list of questions that Amy's been curating for us, and we can get to answering them. Okay. The first question is, this was submitted ahead of time, what equipment is needed to time lock fNIRS to presentation, parallel port, or USB? And can we send a specific character via trigger? Well, I'm happy to answer this one in this case. We did kind of review this in the presentation, but just to go over it, what equipment is needed to time lock fNIRS triggers to presentation? So you're going to use a LPT port, and either if your computer has the LPT port, you'll just connect that directly to the NIRx trigger cable provided, or you can use one of those workarounds. You can install an express card. You can use a Cedar C-Pod. There's various precise timing mechanisms, hardware that you can use to basically convert the signal from a USB to an LPT output. And then as for sending a specific character via triggers, that can't be done with NIRx systems. You can only send integers 0. Well, you can send specifically 0 through 255, but you can't send any kind of characters or strings outside of that. Okay, the next question I'm going to ask David. He's the expert on LSL. How do I test if my LSL triggers are being sent or received on time?
Yeah, that's the question that's frequently asked. There's a couple different ways to do this. The easy but expensive answer is you go to neurobehavioral systems and you pay them about $1,000 for a device called LabStreamer, which was designed specifically to do this. It can do other things, but it's a very, very nifty device that can test latencies and also give you statistical distribution of average jitter time, because the latency will not be precisely the same each time you send a trigger. because it is a software trigger, not a hardware trigger, so it doesn't have the accuracy that a hardware device has. There are other sort of DIY solutions that people do. The really common one is to take a photodiode and tape it to your computer monitor, and then write a script that can, using PsychoPy or a Psych Toolbox or some other kind of programmable presentation software. You can flip your screen from black to white, and then the photodiode gives you an electrical signal that is shaped like a pulse, you know, high corresponding to a bright screen and low corresponding to a dark screen. And you can threshold that and analyze the signal and say when the screen flipped from white to black. And if you're sending LSL markers at the same time as you're flipping your screen, you can make a distribution of how quickly the software markers are being sent. I should say that once liblsl is instructed to send a marker, so that's the bottom under the hood back end of LSL. Once that is told to send a marker, it happens nearly immediately. It's very, very quick. Even if your operating system is overloaded, which in an experiment it shouldn't be, it happens almost immediately. The wiggle room, the unknown factor, is all the stuff that sits on top. So when PsychoPy tells an LSL to send a trigger, that's the part that you might not be sure about. And it's really important that you test these things. If you're doing fNIRS, as Ashley pointed out, accuracy, you have a wide window of time to synchronize a trigger with an actual sample of electrophysiological data, or in this case, optical physiological data. But if you're trying to synchronize with something that's fast moving like EEG, you need to test the latency of triggering, because it can change based on operating system, computer hardware. All these factors can affect the latency. So I would say it's important to test. And it's important to have a device like the lab streamer from NBS, who also makes presentation. It's that company. Or to do a sort of DIY solution, which takes a little bit of engineering craft work, but it's definitely something that's important to do.
Good, thank you. And here we have another fairly common question, but it's a good one. Can I do video integration with LSL? Are there any issues or tricks to making it work smoothly?
That's another frequently asked question. Video is very difficult to integrate with LSL, and for this reason, there isn't a very good sort of out-of-the-box solution. The problem with video is that cameras will drop frames. So your camera may advertise that it runs at 60 Hertz, but in fact, sometimes it doesn't. And this is a challenge. The other challenge with video is codecs. So basically, the way you do video with LSL is you don't actually send the video data over LSL. You write the video data to file, and what you do is you keep track of each frame when it's being written to file, and you call it frame 1, frame 2, frame 3, etc. And that's your LSL stream. And what that allows you to do is, after you record the LSL video frame counter along with your EEG data or your fNIRS data or whatever, you can go back and reference the actual video frames from the file you recorded, which is just a plain old .mov or .afl or whatever. But video codecs will do funny things also. They will interpolate frames, they do a little bit of time stretching, and depending on the codec you're working with, you may encounter problems that you didn't anticipate. These are all excuses for why there isn't a very robust solution for integrating video with LSL. And if you want to know more about this, I recommend checking out the LSL Slack channel. There's been a few lengthy threads about this, and a few developers have tried to tackle this. So there is some stuff out there, but there's nothing that's really quick, easy to use, and just works, unfortunately. It's a very challenging problem, and I don't think anybody's had the resources to really do it properly. It's just a lot of work.
Yeah.
By the
well,
way,
the collaborative nature of LSL, this could be something that is solved in the near future.
yeah, you never know when some lab's gonna put some effort into this and really hammer out a good solution. Another problem is actually operating systems. So it's very easy to do this. Well, it's a lot easier to do this with Linux and OS X because there are some media libraries that make it a lot simpler to do. Windows makes this very hard. Windows, it's very challenging to just grab video frames and timestamp when they're written. So again, it's another challenge that makes it hard to have a robust solution. I just wanted to say, if you are interested in checking out the Slack channel for LSL, there's a lot of good information there. There's been years of support cases that have gone through there at this point. There's a link for joining that Slack channel on the LSL GitHub page. If you scroll down in the README file, you can get an invite, and anybody's welcome to hop on there. And it's also a great resource for any kind of general questions or help. You can often get real-time response from people who are hanging out there and helping people out with LSL.
Okay, great, thank you. All right, let's see. This question I'll also turn to you, David. Are there benefits of using TTL instead of LSL?
Yeah, it's simpler to be sure that your timing is accurate, for sure. You know, hardware triggers are much more stable time-wise, and you can see if it's plugged in or not. From that point of view, it's a lot simpler. On the other hand, not all devices have trigger inputs. So for example, if you're using like a Microsoft Kinect to do some motion capture, or like Elite Motion to do hand gesture stuff, those are really nice devices and can be used in scientific experiments, but they don't have a trigger input. And this is one of the problems LSL was designed to solve, is if you don't have a trigger input, how do you get triggers into your device? How do you synchronize across devices? I think that TTL pulses are always going to be more reliable and accurate than software triggers, but software triggers have their advantages too. So it's a matter of your needs for your experimental design and the devices you're using.
Got it. Thank you. Okay, the next question. TTL is limited to 16 4-bit or 256 8-bit markers. Are there limits to LSL markers? So I will answer this one a little bit. Certainly with NIRx devices, yes, the limit is to those same things. LSL in general, I'm sure it can take more than that, right? It can take like outside of integers 0 through 256.
Yeah, if you want to get down and dirty and write your own LSL code, markers are quite flexible in the type of data they can send. They can actually send anything. So you can send integers, you can send floating point numbers, you can send characters, you can send strings, and you can even send data blobs. So you send a chunk of memory, and it could be anything. Typically, LSL markers are strings, so blue, black, square, things like this. But in the case of NIRx, you're going to want to use, as Ashley pointed out, integers, because that's what their recording software is set up to handle.
Yeah, and you could potentially, if you really, really needed to, well, one thing I suggest people, if they need some kind of strings, like absolutely, you can send potentially combinations of triggers. But what you can also do with LSL is there are some generic recorders. So you can kind of just have the data all recorded in this generic LSL recorder, and then you can also have whatever strings you want then. You're not limited to what the NIRx software requires. So there are kind of ways around this stipulation of NIRx software needing those integer triggers. Okay, I hope that answered that question. Another question, is there a general rule of thumb on how much delay in triggering is considered acceptable in fNIRS? Well, I'm happy to get your perspective on this, David, but I can answer first with like, you generally want to be in the same sampling rate of at least of your data. And that is going to be true for most kind of analysis. So for the general linear model, block averaging, you don't need that specificity of time to the millisecond level. So just as long as you're in the same sampling frame, that's going to be adequate for fNIRS. There are some more complex analysis where you actually might need to know more specific information about timing, like on the tens of millisecond level. And that really is, again, it's just dictated by your analysis needs. But for general linear model, for block averaging, I would say a good rule of thumb is just it needs to be as accurate as your sampling rate. If you wanted to add anything else to that, David.
Yeah, I would point out that, as I mentioned before, LSL markers are very quick. They happen really fast. So a lot of times what happens is the markers hit the data faster than the actual data does. So what I've seen happen, I don't think this would happen with an fNIRS device because it's so well integrated with LSL and this is taken into account already. But I saw a lab years ago sort of using LSL naively, and they were recording EEG and using markers using LSL. And the pathway that they were using for their EEG recording actually had a delay of about 250 milliseconds. So they were getting their markers right on time, but when they went to analyze the data, they thought, wow, we're seeing this new ERP that we didn't know existed at 550 milliseconds. And they were really excited for a second. And then somebody said, well, what's the latency of the EEG? And sure enough, they were just seeing the P300. So you have to take care to know the latency of all your devices, not just your triggers.
Good point. Okay, the next question, do you know any implementations of LSL for embedding systems? I'll turn that to you.
Okay. Some people have done this. I know of a few industry people who have done this. So they haven't, unfortunately, made this available to the public because it's proprietary. The liblsl is released under the MIT license, which basically means anybody can use it anywhere at any time for any purpose for free, including putting it in your software that you sell commercially. So people use LSL and modify it, and then they close the source sometimes. And this is one of those cases. So it is possible, especially now that we have some of these bare metal operating systems that are designed to work on like ARM Cortex chips and things like this. They give you a lot of resources to do what LSL does. But LSL relies a lot on the operating system to give it a lot of its information. So when you strip away pieces of the operating system, you have to make up for that. So you can use the LSL protocol certainly, and you can use parts of liblsl, but you have to do a lot of work to get it on an embedded device. So far, I don't know of any open source implementation of LSL on an embedded device, but there's a lot of interest in that, and I think that's something that we'll start to see soon, particularly because we have these things like Mbed and these other bare metal operating systems coming out.
Sounds good, thank you. Okay, another question from the same user. What could we expect in the LSL streams after a brief network interruption, less than 5 seconds, in the middle of a data acquisition session?
That is a really good question. And that is something that LSL is really nifty with. So LSL is designed to be robust against network and other kinds of data interruptions. And actually what LSL does by default, when you create an LSL output stream, it actually buffers the samples. So for example, if you're sending markers like we saw, just 1s and 2s, if there's a network interruption, those markers will actually stick in the buffer on the output side and wait for the network connection to reestablish, and then they'll fire hose in. So you'll lose the timing if in the case that you're recording in your recording software, like the Aurora software, when the markers are coming. If they're not coming, you don't get them. However, you do have the timestamps, and the timestamps are happening on the trigger output side, not on the trigger receiving side. So you can go back and look at those timestamps, which get saved until the network connection is reestablished, and those don't change. So you can actually reconstruct where the markers should have been. Of course, this is some extra work that you have to do when you analyze the data, but you do keep the information. And the default is usually 6 minutes. So that's enough time if your battery dies or you have to reboot your operating system. If the network connection is somehow severed, you have 6 minutes to fix it and you won't lose any data.
Got it. And are there any kind of this is my own question, are there any kind of network specs that are recommended for running LSL?
Again, LSL tries to be very robust about this. You can fine tune the network connectivity behavior with LSL using config files. That's kind of a dark art in LSL, and it's described in the documentation, but most people don't have to worry about it because the default settings are quite good. In very special situations, wireless networks can be a little bit flaky, for example. It's always recommended to use a hardwired network if you're using multiple computers. So you want to use a local area network connected by cables. It's going to be faster, it's going to be more robust, it's going to cause less problems. So if you're doing something fiddly, you can fiddle around, and there are a few recommended settings for those things, and I believe that's all in the documentation online.
Got it. Sounds good. And I can say in my own experience, I mean, I'm someone who's been in the trenches with some hardware triggering and just have seen the light when it comes to LSL. It can work really, really well in a lot of situations. So it's just to all our users out there, I would recommend it when possible for sure. And so that's all the questions we have for today. Thank you all for your questions. Thank you for joining. Thank you, Dr. Medin, for joining us, as well as Amy in the background there. Just a reminder, tomorrow's session is at 10 a.m. Eastern, 4 p.m. Central on data analysis, and we hope to see you all there. So have a good day, everyone. Bye-bye.
All right, bye.